statistical exercise laboratory, which is one of the problems, of course, when we utilize critical power. So the first test is a VO2max test where we determine maximum aerobic power. And then at 3 to 5, depending how many data points we want to have, 3 to 5 times we ask these athletes to perform time to exhaustion trials, somewhat slightly below maximum aerobic power and above, sort of the literature says 80, 85%, 90%, 100%, 105%. Now these tests are usually in the traditional way, there's a 24-hour recovery minimum in between those exhaustive trials. And this has, of course, major disadvantages. Number one, this is highly time-consuming. Number two, when we work with athletes, it's very disruptive to their training. Number three, what about the reliability of time to exhaustion trials? Now, there's a debate out there. For example, Lawson et al. Says the time to exhaustion trials where an athlete's being put through a test where he or she does not know when exhaustion occurs is not very reliable. Whilst Hopkins et al. Says they've analyzed some of the data and said it is reliable, but I will show you some very new research just after this. But the question of a time to exhaustion trial in itself raises sort of concerns about the ecological validity of those tests. Now this is data that just came out. It's not unpublished. It was presented at the World Conference of Cycling Science. And what was done here is they asked trained athletes and untrained athletes to perform at a relative percentage of maximum aerobic power. And what you can see here, what the range of tolerable durations here is really varied. It's very varied. Now this is the first point, of course. If we want to have time to exhaustion as required for critical power testing, somewhere between 2 and 15 minutes, the data points themselves, if they don't sit somewhere in this range, will cause a problem, as well as very short durations will create a high critical power value, whilst very long duration trials will create higher critical power values. This is one of the limitations that we currently have when we use time to exhaustion trials in the determination of critical power. And therefore, that is one of the approaches that we are trying to follow here. We are setting a time, so we know what we are dealing with, what data points are we dealing here in practice. The typical error, there you go. The typical error, by the way, which Paul et al. Mentions also in their review published this year, is plus minus 5%. Now, if we say critical power determines the boundary between the heavy and the severe domain, and if that is the actual value is plus minus 5%, we are distorting, we have a potentially distorted meaning of the critical power value itself. This is one of the reasons why we would like to encourage future research also to put a performance trial into their research to measure, is it actually critical power we are talking about here? Because when we have, for example, this is one of my athletes here, using the inverse, this is the work time and the inverse time model here, this is marginally, it's only 4 watts. However, 4 watts potentially can, if we go into a critical power of 300 watts, we are talking between 290 and 310 watts. We don't know whether we actually have determined critical power. Where are we here physiologically? Okay, so this is one of the current limitations of the critical power model. When you read research, it is always interesting to see how did they determine critical power. So what sort of exhaustive trial iterations did they use, which model they used as well, and what sort of efforts did they use. And if you look also into the W prime value, again, there are differences. Now, it was 2006, given that critical power is somewhat interesting for research in athletes, a research group from Aberystwyth at the time thought, okay, can we make critical power easier to test, given it is time disruptive, time consuming, training, and so on and so forth.
And exhausting as well.
And very exhausting, yes. So the 3-minute all-out test was developed by Burnley et al. And Annie van Hattelu, of course, it was her PhD. And the idea here is that if you put an athlete through a 3-minute all-out test, that during the first 90 seconds, W prime is already sort of pretty much depleted by down to 5%. So the idea generally is that during the final 30 seconds of a 3-minute test, W prime is fully expended and the athlete consequently can only cycle at critical power. So the test works in a way that we average the final 30 seconds and that N power, at the time it was termed N power, equals critical power. So when W prime is 0, the power that is sustainable at this point equals critical power. The research at the time was performed on a specific ergometer which utilized a particular setting which is called the linear factor, where the power is a function of the cadence. And the idea here is that the athlete reaches the determined power output halfway between the gas exchange threshold and VO2 max. This work, of course, has attracted a lot of research attention, lots of papers came consequently out there. I just want to mention something in